Hello, in today's video we're going to be talking about the octet rule. Now this is going to be our driving rule and driving force for the rest of the semester. It's going to tell us how we're going to create bonds. And we're moving into this world of Lewis dot structures, drawing the atoms, drawing the molecules, and seeing how many bonds are between each of the different elements. So we're going to be abiding by this octet rule a lot. Now there are really two different variations of the octet rule. For smaller elements, we choose an octet rule that really requires the element to only have 2 valence electrons in its outermost shell. That's because these are metals, and we'll see that the smaller you are, so the higher up on the periodic table you are, the more that you're only going to need 2 valence electrons. That's the second rule of the octet rule. The real octet rule states that each element would like to have 8 valence electrons in its outermost shells in this case. And so that's going to be our driving force. Our nonmetals are going to be gaining electrons, and we know that they form anions in order to satisfy this octet rule. And our metals are going to be losing electrons in order to satisfy this octet rule. So I want to take an example and show you the driving force behind this. So let's look at sodium. Sodium is element number 11 on the periodic table, which means that it has a total of 11 electrons in a neutral sodium atom. So let's draw the orbital diagram for sodium and see what we would do in order to get a number of valence electrons to equal 8 in this case. So we know that we have a 1s, a 2s, a 2p, and a 3s. For sodium. And we have further ups, but we're not going to promote any electrons in there, so we're just going to do the ground state of the sodium. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. In this case, these are considered our core electrons. The outermost electrons are considered our valence electrons. So we're going to try and abide by this octet rule. Every atom that's lower on the periodic table than, let's say, lithium is going to need a total of 8 valence electrons in order to be considered a happy atom and a happy ion. In this case, for sodium to get 8 valence electrons starting with 1, it would mean that we would have to add in 7 more electrons in order to get sodium to be happy and follow the octet rule. That's really not going to happen with a metal, because gaining 7 electrons requires a lot of energy. In this case, if we were to drop this 1 3s electron, we could see that we could have a total in the principal quantum number of 2 orbitals, that they would have a total of 8 electrons. So in a metal, it's easier for that metal to lose a certain number of electrons to get a valence number of electrons of 8. So let's see how this works. Sodium plus only has 10 electrons. I'm going to draw the same orbital diagram, but I'm only going to fill it up with 10 electrons and show you that now we have a total of 8 valence electrons. 1s, 2s, 2p, 3s. 1s, 2s, 2p, 3s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We are all out of electrons. We don't use this 3s orbital. There's nothing in it. And now this means that these 8 electrons are now our valence electrons. This is now our core electrons. So we've gone from a set of, what would that be, 2, 4, 6, 8, 10 core electrons and 1 valence electrons for neutral sodium, to now 2 core electrons and 8 valence electrons. The fact that we have 8 valence electrons follows our octet rule, and it indicates to us that metals are going to be losing electrons in order to get to this octet. Okay. Let's take another quick look at a nonmetal. So this is really the driving force of why sodium takes a +1 charge when it forms an ion. Let's look at something such as oxygen, which is a nonmetal, and see what it would have to do in order to get this octet rule. So oxygen is element number 8, which means a neutral oxygen has 8 electrons. 1s, 2s, 2p. 1, 2, 3, 4, 5, 6, 7, 8. Well, look at neutral oxygen. This would be our core electron, core, and this would be our valence electron, electrons. Look at how many valence electrons we have. 2, 4, 5, 6. We have 6 valence electrons. If we were to give up electrons and make oxygen a cation, we would have to give up 6 different electrons in order to satisfy the octet rule of only having 2 in your outermost shell. That's a lot of energy. It takes a lot of energy to strip away all those electrons. It's easier for an oxygen to gain 2 electrons and make a complete 2p orbital to get to our octet rule. So that's why oxygen forms an O2 minus. We now have 10 electrons, 1s, 2s, 2p. Same thing, 1s, 2s, 2p. But now we have 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are our valence electrons. These are our core electrons. And look at this now. Our valence electrons, we have 2, 4, 6, 8. Octet, means 8. So that's one of those prefixes that we learned way back in the day. We're having a number of 8 valence electrons. This is the driving force why oxygen gains electrons rather than losing them. It's easier to gain 2 electrons than it would be to lose 6. So now, you, at the beginning of the semester, ended up memorizing that the metals lose electrons and become cations, and you saw that that group 1 on the periodic table took a +1 charge, but now you know why. It has to lose that s orbital electron in order to satisfy this octet rule. And we knew that oxygens, these group 6a nonmetals, would gain 2 electrons, but we never knew why. This is the reason. It wants to fill up a completely filled 2p orbital in order to satisfy our octet rule. So we're going to be doing a few of these in class tomorrow. That's all I want to discuss today. And with that, I want to say have a great night. I will see you all in class tomorrow.